In this video, I want to cover the topic of copula fitting, but in R. So we've covered the conceptual things that have to do with copula fitting. You can maybe try to run those codes yourself to make sure you understand how they work. But I have those slides here that are hosted on online. Okay, so in essence, I just want to do what we've presented theoretically, but I want to do it with a simple example. So this is not like an exhaustive lecture about copula fitting. I just want to illustrate what we've done, what we presented in the theory part. Just as a note, there's this package in R that I'm going to use quite a lot. It's a quite popular package. It does a lot of things that have to do with copulas. The package is just called Copula. You can find it easily. And you can consider that what we do here is a sort of case study. I'm going to illustrate all the methods we've mentioned with a specific example. And the specific, so here specifically, I will generate some data with R that has, of course, a specific dependence structure and some specific margins. And so here in this case, the dependence structure is the Clayton copula, and I'm just picking pretty much arbitrarily exponential margins for the univariate variables, and it's just going to be an example in 2 dimensions. So I'm just generating x1 and x2. They have the Clayton copula and they have the exponential margins. And again, the overall goal is to fit the copula to this data. Meaning, in reality, I know it comes from the Clayton, but if I imagine I just see this data and I want to fit a model to it, so I want to fit a specific copula to it, how do I estimate the parameter of this copula? Okay, in R, so I use this library copula. I'm going to set the seed so my results are reproducible. Arbitrarily, I set a sample size of 1,000. So this means I have 1,000 points, 1,000 observations of the bivariate x1 and x2. Okay, again, arbitrarily, I set theta to be 6. I believe this means the Kendall's tau between my data is 75, but 0.75. Now in R, you can simulate with the package. You can simulate with R copula. The syntax here doesn't matter too much, but this is the sample size. This is a keyword Clayton copula. So I'm telling, okay, I want data from the Clayton in dimension 2 with parameter theta. Now this automatically generates uniform 0, 1. It generates uniform 0, 1. Okay, U1 is the first column of this thing sample, and U2 is the second column. Now I want data that has exponential margin, but that's easy to obtain. You know that if you feed a uniform to a quantile function, you obtain a random variable that has the distribution characterized by this quantile function. So the quantile function of the exponential, if I feed to it uniforms, this thing x1 will be an exponential here with parameter, the rate parameter being 1. Okay, well, this means a uniform, an exponential with a mean of 1. And this, just arbitrarily, x2 is then an exponential with a mean of 2. Okay, 1 over the rate. Okay, let's just now see what the data looks like. Okay, U1, U2, remember, is generated from the copula, so it's exactly uniform variables. So they're between 0 and 1. And following the Clayton copula, not very surprising, there is here what appears to be lower tail dependence. So the dependence overall is quite strong. There's a trend here that the overall, the bigger the U1, the bigger the U2, but the trend is stronger in the for small values. Okay, so there's lower tail dependence. Okay, now if I look at my x1 and x2, so remember x1 and x2 are just the transformer version of U1, U2 to obtain exponential margins. Okay, now it looks quite different. Well, yes, because an exponential is not between 0 and 1, it's between 0 and whatever. Here, the max value for the x1 is a bit bigger than 8, and for whatever reason, this is just a random sample. The max value for x2 is almost 14. And here, I think this highlights the fact that dependence is easier to see on the uniform scale, because I think I mentioned this before, but you know that under independence, you expect a square here where all the points are uniformly distributed. So you don't expect more points here and more points here compared to here. So here you see the dependence quite clearly. Here, the fact that the margins are not uniform, it's harder to interpret what dependence is. But anyway, that's just a side note. just some statistics. So the regular correlation, so you can obtain this with core, so that's a function in R, core x1, x2. Of course, x1 is a vector of point, x2 is a vector of points. You get the sample correlation. So this is empirical estimation of the regular correlation 0.7. For Kendall, you get close to the theoretical value, which would be 0.75. With method Kendall, here you get 0.7544, blah, blah. And for Spearman, you get actually substantially bigger. So I don't have good explanations for this. It just highlights the fact that, the explanations for why they're kind of different here, but it highlights the fact that they're not the same thing. Although they have similar properties, Kendall's tau and Spearman's rho, they're different measures of dependence, so they might give you different results here. Although, of course, here the general idea is that it's substantially positive, right? Which of course is highlighted by this this plot. It's increasing. U1 is increasing in U2. Okay, that's just a bit of preliminary analysis. Now, again, the goal here is to apply the methods we've seen for Copula fitting, and we've seen a few. The first one was kind of the more simple one, which is to simply match the pick the parameter that matches the empirical Kendall's tau. So it's not hard to show that within the Clayton copula, the theoretical tau is equal to the parameter divided by the parameter plus 2. So then you can, and this is actually done. This is one of the tutorial exercises. Okay, to show this, it's not very hard. Then you can invert this this formula, meaning you express the parameter as function of tau. And why you do this? Well, it's because tau is easily obtained. The empirical tau is easily obtained when we just got it here. Okay, so then that's a first method to estimate the parameter theta of the Clayton. You plug here tau, the empirical tau. Now I should have mentioned. Okay, what we do is that we want to see if the methods we have to fit the parameter of the copula work. So I generate data that is exactly Clayton, meaning it has the Clayton copula, and I'm going to assume. So I'm going to assume that I'm fitting the Clayton there because I want to estimate the parameter of a copula. Because I do that for pedagogical value. I want to see if I'm going to get the right parameter. I could do other things. I could say I generate the data from the Clayton, and instead I'm going to fit to it a Gumbel or whatever other copula. But those are bad choices, right? And then I could see goodness a fit for that. But that's not the point here, or the objective. The objective is the data is exactly Clayton. Let's fit the Clayton to it and see if we get good results for the parameters. Okay. Okay, so let's try. Very easy, right? Again, I'm just applying this method. Okay, so I know what the empirical tau is, so I plug it here in this formula, and I get my estimate of theta following this first method. And in fact, here it's not too bad. It's not too bad. Now, as a comment here, of course, this is a random sample. I could do this again, and I would get a different value here. Maybe it would be worse. So I'm going to show all the methods once, but then at the end, I'm going to repeat everything 1,000 times, and then we get a better judge of which method is better. Okay, so first we apply all the methods, but at the end, we do a sort of a little study to see overall, if I repeat this 1,000 times, what do I get? Okay, because again, the point here is it's hard to see. We cannot really say if this method is good overall because it's just one value. Maybe I do this again and I get something far from 6. But yeah, but at least for now, it seems okay. It seems okay because again, I know the copula is Clayton because I generated the data from the Clayton with the parameter theta equals 6. And on one sample using this method, I get something not too far. Okay, so let's keep going and let's see the other methods. By methods, maybe it's worth to take a second to just remind you on the slides what I'm talking about. I'll go back to the slides for a second. Okay, so here in this section, copula goodness fit. Now I've just presented this approach that I called some sort of method of moments approach, right? Just replacing the tau by the empirical value. But now we're going to see the maximum likelihood. But remember, there were a few different options. First, we're going to see fitting the copula and the margin separately. So using this idea of pseudo uniforms, And I'm going to do that actually in 3 ways. Actually, I'm going to do that with the empirical CDF of the margins. Then I'm going to do that with a fitted parametric model for the univariate CDFs. The right choice, which in this case is exponential. I'll do that with a bad choice to see what happens then. And then lastly, we're also going to apply the other method, which is to fit everything together. So that's what I'm doing now in R. Okay, so first is, using pseudo-uniform, so fitting the margin separately, and now fitting the copula using those pseudo-uniform observations. Now to do that, to do maximum likelihood under pseudo-uniforms, I need the density of the copula, because remember, a copula is a CDF. Okay, it's not a density, but you easily obtain the density by derivating the copula twice. I haven't done the details here, but you can check this for yourself. If you derivate the Clayton copula twice, meaning one time with respect to the first argument U1 and another time with respect to the argument U2, you get this this expression where th here is short for theta, okay, the parameter theta. Okay, now that I have that, I'll be able to apply a maximum likelihood. Now, what I need is a sample of pseudo uniforms. Now, using the empirical CDF method, that's extremely easy to obtain. You can simply define U1, so the sample from U1, sample of pseudo uniforms. You can take the rank of your initial variable, x1 in this case, divided by n+1. Let me explain why this is, okay? And I've added the slide in the PDF. Okay, so what I'm saying here is that where are my pseudo uniforms? They're here. Okay, so I want to obtain my sample of pseudo uniforms called here well, in our case it's simple. We have only 2 dimensions, right? So here this in general goes from dimension 1, 2 up to k, but here we have uj1, uj2, and that's it. Okay, and again, j represents the observation. So for us, we have 1,000 observations. This is f hat 1 at the observation xj1. But now in the first method, f hat is simply the empirical CDF of the first variable. Okay, so what I have here, I just said in the R that I'm taking the rank of x1 divided by n+1. Why do I do that? I've added a slide over there just to explain. Here, okay. So I'm saying u hat j1, which is just by definition f hat 1 xj1, is going to be, okay, it's going to be rank j1, sorry, rank xj1 divided by n on the R I had n+1. Now here I have n, but let me explain. What is, and don't worry about xj2 because it's exactly the same thing. What is f1 hat xj1? Well, f1 hat is the empirical CDF. So it's simply the number of observations that are smaller or equal to xj1. Okay, but the number of so here this is this line, the number of observations. Okay, I call this directly hash xi1, the number of observations for the first variable that are smaller than xj1. Well, by definition, this is the rank of j1, the number of observations that are smaller or equal to xj1. Well, yes, because if xj1 is the very smallest observation, the number of data points smaller or equal to xj1 is 1, only itself, and then the rank of xj1 is 1. Okay, if xj1 is the second smallest, well, then 2 points are smaller or equal to it, and then its rank is 2. Okay, and then at the end, of course, divide by n because it's an empirical CDF, so it's a probability to be smaller than whatever argument is here. Now, this explained, but this means you would expect to have rank xj1 divided by n. That's not what I had in R, and for xj2 you have exactly the same thing here. But let me go back to R. In R, what I have is, okay, I take the rank of all the x's divided by n+1. This is just to avoid problems. It doesn't make a big difference because, of course, if n is moderate to big, divide by n or divide by n+1 doesn't make a difference. or not a significant difference, but it's a common practice to divide by n+1 because of potential boundary problems. It's just the case that some copulas are not well defined at their boundary, because remember, a copula is a CDF of uniform 0-1 random variable. It is just the case that sometimes you have problems to evaluate the copula at exactly the boundary 1. So you want to avoid to have pseudo observations that are exactly 1. And of course, if you had divide by n here, well, the largest here would be n. Divide by n, you would have exactly 1. Okay, so this is just a technicality to avoid problems, which is very, very common to do that. Okay, now let's go. What I've done so far is I've created my pseudo uniforms. Let's just plot them. Okay, those are the pseudo uniforms. To the naked eye, this looks extremely similar to the real uniforms I had before. Okay, but by what I mean by real uniforms is simply that when I do this sample R copula, I generate exactly uniform 0-1s. But now, and here I've created exponentials. Then from the exponentials, I create my pseudo uniforms following the empirical CDF method, but I obtain something that is, at least a naked eye, very similar in terms of dependence pattern. Okay, but now let's apply the fitting. Let's do the maximum likelihood using our newly generated sample of pseudo uniforms. This is just good old maximum likelihood. So let me go quickly over this. I create a function here that's going to be fit Clayton. The arguments are simply my my observations. So U1 for all the values of U1 and U2 all the values of U2. Negative log likelihood. So it's a function of, here in this case, there's only one parameter because there's only one theta to fit. This is simply the negative of the sum of the log. D Clayton, remember, it was simply my density of the copula. It's a density function with uniform margins. Now, of course, it's a bivariate density function, so it has two arguments. Well, two arguments and then a parameter theta. Okay, and so when I sum the log of the density at every argument, at every data point, I get what I want, the log likelihood, well, negative log likelihood, that I can then minimize. Of course, I maximize the log likelihood, which is equivalent to minimizing the negative of the log likelihood. I'm gonna, as usual, feed an initial estimate to the minimization. The initial estimate, why not? We have a very good first guess, which is the one based on the empirical Kendall tau. Okay, so this is the one I've computed before. Following this formula here, twice tau divided by 1 minus tau. So this is my initial value for the optimization. Okay, and then I apply my NLM function to what? To the negative log likelihood at the initial value for the parameter of this thing. Okay, and I return my my fit. Okay, let's try. Fit Clayton. Okay, this is feeding my sample of pseudo uniforms that were over there to this newly defined function. Okay, I get something extremely close to 6. Now, again, this doesn't mean the method is always excellent because I just have a random sample. But here in this specific case, okay, yes, I found a parameter that's extremely close to the real value, which is 6. Okay, but now let's try the other methods. Again, other methods would be applying this maximum likelihood, but with different ways of finding the univariate CDFs. So to obtain a pseudo uniform sample, another possibility is to parametrically fit the margins. Okay, so just look at the data, say, okay, the margins look like they have a specific distribution. We fit that distribution, and then we use this fitted CDF to compute our pseudo uniforms. So now we do this with a good choice for the margins and a bad choice. Now, let's assume first that we have the right choice for the margin. So meaning we fit our univariate observations to the exponential by maximum likelihood. In the case of exponentials, the maximum likelihood estimator of lambda is just 1 over the mean. Okay, so my x1 sample is an exponential. I assume that I know this is exponential, so I'm going to fit the exponential to it. First parameter would be, well, the parameter of x1 would be this. Parameter of x2 would be this. And then again, once I fit my margin, I create my pseudo uniforms. Okay, so I create my pseudo uniforms. Just to be clear, let me go back for a second in the slides. So I'm back to this step here. of creating my pseudo uniforms U hat, but my F1 hat is now the exponential that I have fit to the data, meaning with a specific value estimate for the parameter, and inside I feed to this F hat, which is again now the fitted CDF of an exponential. I feed it X. Well, I feed it all the observations. So back to the R. What I do is simply Px, this is the CDF of an exponential. Pf of x1, now I create my sample of pseudo uniforms with parameter, of course, the one I fitted, here, my estimator of the parameter. Okay, I do that for U2 as well. And now I call my function fit Clayton, which was the function I defined here to find simply the maximum likelihood estimator based on a pseudo uniform sample. Okay, and I get something pretty good as well. Okay, relatively close to 6. But again, this is based on one sample. We'll do that at the end for 1,000 times, see what happens. Okay, and again, of course, this was the correct choice. Now, in reality, no one tells you that the data is exactly exponential, right? This is like just a toy example, if you want, or a situation where we want to check if the method is correct. So we cheat because we know the data is really exponential. But let's see what happens if we have a bad choice of margin. Let's just say that here I don't make any analysis or preliminary checks, and I just say, I think my data is normal. Let's just use the normal. So I fit my x1 and x2 to the normal. So I obtain the normal, of course, that's 2 parameters. So for x1, I get the mean of x1, and then I get the standard deviation, which are the parameter mu and sigma of the normal. I create my pseudo uniforms using this bad choice for the margins. So again, same kind of thing. P norm of x1 creates my sample of pseudo uniforms, and P norm of x2 creates my sample of uniforms for U2. I again fit the Clayton to this pseudo uniform data, and now it's not as good, right? It's not. I suppose it's not terrible, but the value is certainly more off than all the other methods we've seen. Okay, now which is not too surprising. It's not too surprising because my choice of margins here is terrible, which means that my pseudo uniforms here, U1, U2, are probably quite far from being really uniforms. And that's in fact the case, and I can check because I can plot the histogram of U1, and that's on the next slide. You see the histogram of U1 is pretty far from being a uniform, which makes sense because I haven't used the right CDF in my transformation. Okay, I haven't used the right CDF in my transformation. Okay, let's continue, and we have one more method to see, and this was fitting everything together. And this is just to make sure we agree, we're clear in the slides. This is the method here. Here we can fit everything together because I said you can find, at least in theory, the density function of your x's as a function of the Copula density. It's just this formula here. Is the Copula density, little c, careful, this is little c, not big C. So little c of all the margins times the individual margins, that is the density of your x. And so this is a density that contains all the parameters of the Copula, in our case theta, and the parameters of the margins, in our case lambda 1 and lambda 2, because our 2 margins are uniforms. So you can maximize this by maximum likelihood. Let's see. So just as a comment here, this will work because it's not overly complex. So we have only 3 parameters. Okay, 1 parameter for the Copula and 2 parameters for the margins. But in reality, this gets messy very quickly because if you have a big model with more than 2 variables, maybe the Copula has several parameters, that it gets a lot of parameters. So you might not be able to optimize this. And also there's a danger that here, because you fit everything together, you haven't done any checks to see if the fit of your margins is correct, right? So you could kind of too naively apply this method and end up with the fit that's not bad because you haven't checked that your choice of parametric model for the margins is correct. Okay, so let's do this now. Density Clayton exponential. This is just the density as I just shown on the slides. Density of the Clayton in which you feed the CDFs of your margins. The first one is p exponential, p exponential again for the second, and then you times again density of the exponential and density of the exponential. Now note here, I'm fitting everything together. I'm making the right choice. Okay, I'm picking the correct choice of margins for x1 and x2. Maybe I should have tried to do this with the incorrect choice. I haven't done it here, but yeah, maybe some other time we can do that. But anyway, fit Clayton exponential. So that would be a new function I define, well, to apply maximum likelihood. Now it's the same thing. It's just that I have 3 parameters, right? So I have 3 parameters to fit at the same time. So it's a function of p, but p is a vector, so p1, p2, p3. And the first one, well, okay, the first parameter is the Clayton Copula parameter theta, and this is the parameter for the first exponential. This is the parameter for the second exponential. Okay, again, I give initial estimates. For tau, I know how to do this. Well, I found tau, then for theta initial, I give the same estimates as before, and same thing, I have good guesses for the parameters of the exponential because I can just apply well, method of moments, for example, or in this case, it's also maximum likelihood for margins, parameters of the margins, I mean. And at the end, same thing, my function NLM of the negative log likelihood evaluated at the initial values will give me my estimate. Let's try again. X1 and X2 is my sample from before. This hasn't changed, and I get something pretty good. Again, for the parameter, the real value is 6. I'm not too far, and for the individual parameters of the margin is pretty good because again the real values were 1 and 0.5. Okay, this is just to illustrate how to do that. Now, okay, before, as I said, we're going to do that 1,000 times and see what happens, so we can compare really the methods. But before I do want to present how to do a goodness of fit test, because again, here in the textbook situation that I know the copula is Clayton, and I try to fit the Clayton to it, meaning my data has been generated under the Clayton copula, and I fit the Clayton to it. Let's just see how you apply goodness of fit. Again, this is just applying the Kramer von Mises test statistic, but in this package copula specifically, so this is a package, the specific function GOF copula has a few different options that you can explore. The documentation on this package is relatively documented, so you can check for other options. But here, let's just use the method SN because this method corresponds to the test statistic I presented on the slide. So let's try that. So the syntax here is simply, okay, I think there's the way to find p-values, I think uses some bootstrap method that has a number of replicates, but so this is why I'm putting replicates equals 500, but doesn't matter too much. Where do I use replicates? Ah, yeah, here, reps. So I need an argument here. I think you can put something else, 1,000 or something. Then, okay, I'm gonna try the Clayton. So here, this simply saying, okay, test that your data conforms to the Clayton copula. Okay, so H0 would be my data as the Clayton copula. I feed it here on my data, and then reps, that's fine. SN is just the method, and this don't worry about this. Okay, and then what do we get? I've fed data that is exactly Clayton. I should not be rejecting, and indeed the p-value is big, so I'm not rejecting. But let's try again. Now I'm testing if the Gumbel is a good fit for my data, good fit for the dependence of my data. I feed it the same observations, and now what happens? The p-value is very small. So the goodness of fit test works because it's rejecting that Clayton is a good model for my data, and I know it's a bad model in this case because, of course, I know that the data is in fact Clayton. Okay, and you can try again with here. Let's test: is the Frank copula a good copula for the dependence in my observations? Let's see. No, p-value is very small. Again, you would reject that Frank is the copula of the data. Let's try it one more time. Is the normal copula, this is what I call the Gaussian copula in the lecture, is that a good model for the dependence on my data? Apparently not, because again, the p-value is very small. Okay, so this is just to show you how to apply this goodness of fit test in R. Okay, now with this done, let's let's repeat everything, as I said. So to sum up so far, we have fitted the Clayton copula to a single, to one randomly generated sample, having exactly the Clayton copula. If we have done this on a different sample, we would have obtained different estimates. So we repeat all 5 estimation methods. Remember, yes, we've done 5 different things. The first one was like the method of moments. Then we had pseudo observation, pseudo uniforms from the empirical CDF, pseudo uniforms with the good fit for the margin, which is exponential, pseudo uniforms with the bad fit, which is the normals, and lastly, the 5th method was fitting everything together. Okay, fitting margins fitting correct margins and copula together. So this is 5 methods here. This video is starting to be a bit long, so maybe this you can review the syntax in your own time if you want. I'm just creating a function that's going to do exactly the same thing. Wait a second. Oh, no, sorry. I'm just creating a function that applies. I've lost my slide. Okay, so over there, I'm just creating a function that is applying all 5 methods to the data. Yes, I believe that's what I'm doing. And returning the results at the end. Okay, meaning if, and this, you know that maybe it's not the best syntax, but I'm not here in this function. I assume the sample is declared somewhere else. I'm not passing a sample to this function. Maybe it would have been better syntax to do that, but anyway, I'm just assuming the sample exists. Sorry. No. I'm creating the sample here. Sorry about that. I got confused in my own code. So here, first step is do what I did before. Okay, I generate a sample from the Clayton. This is a uniform sample, but now I'm transforming it to specifically exponential margins, with the first one is as a parameter here and second one as this parameter. And then I apply all my methods, meaning I fit the theta with the Kendall method, then I fit the theta with the empirical CDF method, then I fit the theta with the exponential margins, then I fit the theta with the normal margins, and then I fit the theta with the full maximum likelihood in one step. And then I return the results. Okay. I do that once. This is going to generate one sample, and I get those values. Okay, this in fact is exactly the same values I obtained kind of manually or step by step before. Okay, but now I repeat this, as I said, 1,000 times. Now, if you do that on your own computer, this actually takes a lot of time. I think it takes a couple of hours to compute everything, 1,000 times. Okay, so I set the seed. Okay, I want to do this 1,000 times. I create this results, which is a null matrix with nothing, and then I'm going to populate this this metric with my results. Okay, for 1,000 times, I'm going to put in results the estimate theta, which is the call to this function that does it once. Okay, so the function does it once, but I call the function 1,000 times each time I store the result, and then I can try to analyze overall what I get. And overall what I get is simply this. Remember, the goal here is to fit the copula, is to obtain the parameter theta. There's only one parameter. So once I've applied my results, once I've obtained 1,000 times my result based on 1,000 samples, I can summarize them on using box plots. So remember, first method is just the method of moments. What is the box plot showing? It's simply the 1,000 values of the parameter theta. This line is the median. In this case, I think the median is probably very close to the mean. Okay, and this bar is then the 75th percentile of all the values, and this one is the 25th. But overall, what we see is that all methods give reasonable results. Reasonable because it seems that the median is close to 6, and 6 is the real value of the parameter. All methods except, of course, the one with the incorrect choice of margin. So, and that kind of makes sense because all the methods then rely on a good choice. This is really the one that if you've picked the wrong margins, meaning that you have obtained pseudo uniforms based on a totally incorrect fitted f hat, then you get results that are nonsensical in a sense, because when you fit the copula, well, you fit a copula that you assume as uniform margins, but in this case, the margins are totally not uniform, so it's not very clear what you're doing actually. And you in this case, you get results that are pretty far off the real value of the data parameter. But now, one last comment. You look at this and you might say, the method 3 and the method 5 seems to be the best because they have a slightly smaller variability in the results. That might be true, but those are idealistic methods because here we assume we have fit. Well, this method relies on the fact that we have chosen exactly the right choice for the margins. Okay, and this choice, again, same thing. When we maximize the full likelihood, we have picked exponential margins, which is exactly how the data was generated. But in reality, you don't know what the margins are, so you might make a choice that looks good, but might not be as good as you think. So the point is just this. Don't conclude that this method and this method are always the best, because this is an idealistic scenario where you exactly know what the margins are. I would say this method, using just the empirical CDF, is pretty damn good because it doesn't rely on you knowing what the margins are. You just pick the empirical CDF of the data, and you still get that the median value of the parameter estimation is pretty close to the real value 6. Okay, and you get a variability that is well, it's still there, but I suppose it's not terrible. And in fact, this method is also pretty good in this specific case, right? Because it's also right on point on average. Okay, and I think this explains why it seems to be that using empirical CDF to estimate the copula parameters seems to be the preferred approach just across the board from what I have seen around. Okay, I believe that's the end of this video, which is starting to be a bit long. Those comments, let me just review them. I think I've said them. All methods produce satisfactory result except the method where margins were fit to a completely wrong distribution. That's not very surprising. Method 3 and 5, where we assume correctly exponential margins, are in idealistic setting because we have picked exactly the right margins. Okay, in reality, you don't know that for sure. In contrast, method 1 and 2 also give good results, but are not relying on specific knowledge about the data generating process. Okay, so maybe in general they would be preferred, I would say. That's maybe my opinion. Okay, I better stop here. I know this is quite a lot. Perhaps it's a bit heavy in content. If you have any questions, of course, send them my way on the discussion forum. And I'll try to give you a few exercises in the tutorial to practice this. Okay, so thanks so much for listening. Bye for now.